So in this session, I will be discussing control charts for attributes. Okay, so I've already mentioned that why do you use the attributes data, and when you use attributes data related to the quality characteristics, so you need to use this set of control charts exclusively designed for the attributes data. So in this particular session, I will be discussing about different types of the control charts in use, along with now their OC curves, that means as a performance measure, and with examples. Okay, so we have already mentioned that there is the P control chart for the proportion nonconforming. That means your purpose is to control the proportion nonconforming. So how do you define this proportion nonconforming? That means if the sample size is n, and out of n, you find x number of the nonconforming units, they are not acceptable to you, then obviously the proportion nonconforming is P hat is equals to x by n. And this the P, the proportion nonconforming, is assumed to be following a binomial distribution. Is it okay? So here I have clearly mentioned x is the number of nonconforming items in the sample, or the items or the units, n is the sample size. So now in many cases we will find that whenever you deal with the attributes data, many companies they feel like using a P control chart. So as I have already mentioned that at the top management level you can use it, at the middle management level, and even at the operations management level you can use the P control charts. Okay. For example, the management of the chief executive officer of a company can be evaluated by considering the proportion of non-conforming items produced at the company level. Like say, on an average it produces 3 to 5% non-conforming. That is the company level. So in order to control this proportion non-conforming, okay, of the output, so you may feel like using P control chart. So a P chart can provide a source of information for improving product quality. It is obvious. How to construct a control chart? There are certain steps. First, you select the objective. What is the purpose of using the control chart? So the details are here, and at which level you will be using the P control chart. So this should be made very, very clear. Now the next important selection is that you need to determine the sample size and the sampling interval. That means how frequently you will be collecting the sample, the sampling frequency or the number of samples. Now as such there is no formula for determining this. So but one formula is that as you are dealing with the attributes data, are some rules. Don't say it's a formula, it's a rule, that as you are dealing with attributes data, that means the exactness in the information is missing. So what you need to do, that means usually that means the sample size must be on the higher side. Is it okay? So that is one say the guideline. And the second guideline is you restrict to the number of the samples in such a way that you can capture in almost all sorts of situations, okay, that are occurring. Is it okay? That means instead of collecting data only for one day, why don't you collect data at least for 1 month? That means a month is a representative, and if you consider 25 days in a month, or say 30 days in a month, you say that within these 30 days I am facing all sorts of situations, and the process performance is influenced by all these situations. So this is the basis, and this way you determine, in fact, these rules you follow. Then the step 3, you have to collect the data and record on an application form. Many a time, you need to design the data collection form. At the step 4, calculate the center line and the trial control limits. Is it okay? So, for that you need to use the formula, and when you use this formula, there are two kinds of situations you might come across. The first one is the no standards given. That means right now you have started the process and the process has become stable, and we say that first the stability condition you have to meet, and once the process becomes stable, then only you assume that this process may be a controllable process. Is it okay? So, you may think of the concept of stability. That means what are the features in a process that you may observe indicating of its stability. So that is the first point to be looked into. This is a very good assignment, in fact, for any kinds of process. Once you declare the process to be a stable one, then you say whether it might be assumed that it is a controllable process. Now, if it is a new process, is a stable process, controllable process, but there may not be any standards. So what you need to do, you have to start from the scratch, you have to collect data, and in a systematic manner, and so in this case, that means the no standards or the target value of the proportion nonconforming is specified. It's not known. Okay. So for that you have to collect data. So what you try to do, first you collect data and you calculate based on the data the average proportion nonconforming p bar. Okay, so how do you collect this? That means suppose there are g number of samples, and for each sample the average value is, for the ith sample it is pi hat, and so the average is this one. Now how do you get this pi? Obviously for each sample, say ith sample, you have x number of the non-conforming, xi number of non-conforming divided by the n or the sample size. So that n is over here and n is assumed to be constant. So this formula you use, and so this is basically the center line for the p control chart. That's why CL subscript p. Then you determine the upper control limit for the p chart as well as the lower control limit for the p chart. So G represents the number of samples, and since the true value p is not known, this is just an estimate. So the value of value as given by 5 is used as an estimate. Is it okay? So it is not known. That means standards are not known. In accordance with the concept of 3 sigma limits, the control limits are given by this one. That means the proportion, that is p, is assumed to be binomial distribution. So this is the formula you use for binomial distribution assumptions. So this is the standard deviation. So this is your the average the center line plus 3 times the standard deviation value. So here the value of k is 3, and similarly the lower control limit on the other side, is it okay, p bar minus 3 times the standard deviation value. So what is the standard deviation value? Root over p bar into 1 minus p bar divided by n. Okay, so with binomial distributional assumption. Okay, so you refer to equation number 6. Then if the standards are given, what do you need to do? That you don't need to calculate p bar, because already the standard is given. That means the target value is mentioned. So suppose the target value, based on your experience, suppose you are running the systems for a long time, is it okay, you are aware that at a value of p0, is it okay, the process is around this value, the process is running. So that is referred to as the central line, that is p0, is pre-specified. And so once the p0 is known, that is referred to as the standard, obviously you can determine upper control limit as well as the lower control limit. So you use the same formula, only the instead of writing p bar, you write p0, that is the standard is given, and 3 times the standard deviation. Is it okay? So if the lower control limit for p turns out to be negative, in many a time there is a high probability that that lower control limit may be negative. So negative as such doesn't carry any meaning. So what you need to do, that means the lower control limit is simply counted as 0. Is it okay? So make it 0. Now my question is, this is an important the question that why do you make it 0? Okay, why don't make it let it the remain at minus value? Is it okay? So this may occur not only for this kind of control chart, for any kind of control chart this may occur. So always it's a right approach that that we make it 0, convert into 0. But there are certain cases where the negative value has a meaning. So again, so when we refer to a special case in control charting, so we'll discuss this aspect. Is it okay? So this is the standard givens. Next we go to step 5. Calculate the revised control limits. So what you try to do first, you control limits. These are basically the preliminary control limits, and then you draw the control chart. And suppose you are dealing with some 25 sample points. So these sample points are plotted. Is it okay? And then you analyze the plotted values and the pattern of the plot for the out of control condition. Typically, one or few of the rules are used concurrently. On detection of an out of control condition, identify the special cause and propose remedial actions. That means you may find that suppose you are dealing with some 20 samples or 25 samples. So all these 25 and the sample points will be plotted, sample values will be plotted, and you may find that 2 or 3 sample points are basically are plotted outside of the control limits. So you have to remove those 2 or 3 values from the list, assuming that they are due to the occurrence of assignable causes. Assignable causes are identified, and then the remedial actions or the corrective actions are taken to remove those causes. That's why these points are removed. Okay. Now with the remaining points, again you calculate the revised central line. Same formula you use. Only thing is this value will be different because already you have removed those points which are found as out of control points in the list, and similarly upper control limit and lower control limit. Is it okay? So so the for P charts based on a standard P0, the revised limits do not change from those given by 8, obviously, because you don't need to collect data. Is it okay? So you just construct the control chart with the standard and you start using it. Is it okay? And then you have to implement the chart. Is it okay? So implementation means, okay. Now here is an example of P control chart, right? So the date wise you collected the data, and the number of inspected items is all 50. That means here the sample size is 50 and sample size remains constant. The number of non-conforming items that you note down these values against each sample. So the total is 90, and the total number of the units inspected, that is 1250. So individual, the sample wise, you can calculate the proportion non-conforming. Is it okay? So and against each one, these values are very high compared to other values. Is it okay? So you just note the points. In fact, you write down the points. That means the drop in pressure, sudden. Is it okay? That's why the value is like this, 0.20. Is it okay? So this may be considered as an outlier. And then you calculate the average proportion non-conforming, 90 divided by 1250. Then you calculate the central line. You calculate the upper control limit, and you calculate the lower control limit. The lower control limit is actually it is found as negative, and that's why it is converted to 0. And we are assuming that the control limits are at plus minus 3 sigma limits. As we have been saying all the time, that unless otherwise specified, the control limits are assumed to be at the plus minus 3 sigma limits from the central lines. So okay, so this is this way you calculate, and then you plot this data. Is it okay? So this point is found as non-conforming. Is it okay? Not non-conforming, out of control, and that's why this point is the removed. Is it okay? The sample 8 is deleted, and then that means the number of nonconformities, number nonconforming in that particular sample 18 was 10. So the total number is 90 minus 10 divided by 1200. But that means it was 1250. So one sample is removed. Is it okay? So it is the revised value of the center line, and similarly the revised value of the upper control limit as well as the lower control limit. Is it okay? Are computed. These two values are computed. Is it okay? And we find that the remaining samples are now in control. So that is the final control limit. So if in this case what we have found that this is a second example, that means a standard is set. That means what is that standard? The value of P0, it is 3%. So please go through this example, and you will find that here we have assumed that the sample size is 100. It's quite common when you deal with the attributes data and you use the control chart. So usually it is at least 25 the sample size whenever you deal with the control charts for the attributes. So this is just an example, and again, this particular sample you will find that the number of non-conforming items is significantly more, and that's why the die not aligned. There is a specific reasons. As a process engineer, you must be able to identify. Is it okay? That is your job while you construct the control chart. And obviously, in many cases, this may be considered as an outlier. So what you try to do, first you calculate the PO is 0.3, and then based on this you calculate upper control limit, lower control limit, and straight you start using the control chart. So all these values are plotted. Is it okay? And you find that these two sample points are plotted outside the upper control limit. Is it okay? So this, and then you start interpreting whether you observe any plotted patterns or not, whether this behavior of the process is systematic or non-systematic. So this way you calculate, all these details are here, and the sample 8 is eliminated. So obviously you have these P bar values, calculate, okay, you recalculated these values, and then again you calculate the center line, upper control limit, lower control limit. Again you find the lower control limit is negative, so it's converted to 0. So the remaining samples, including sample 11, would indicate a process in control with the point hovering around, with the points hovering around 0.039. That means the process is around, process exists. That means process is performing around this value 0.039. Is it okay? So the calculated average. So that is the interpretation. When you refer to the C chart, now the C chart, when you use C chart, you are trying to control a non-conformity. So what is a non-conformity? Non-conformity is nothing but the defect. Is it okay? So a product, an item may have the several kinds of the defects. So it is your responsibility to identify these defects. Is it okay? Against a particular item. So a non-conforming item, that means a defective item, may have one or more non-conformities that make it non-functional. Like so suppose in an automobile, if the engine becomes the defective, the entire system, the entire automobile becomes defective. Whereas suppose there is say certain defects in other components, like say the seating arrangements and all those, like on the dashboard, and those defects as such do not affect the performance of the product. In that case, the performance of the vehicle. Is it okay? In that case, even if there are many defects or non-conformities, the product as such is never considered to be non-conforming or defective. So there are many such instances you will find. So a C chart is used to track the total number of non-conformities in samples of constant size. That means sample size doesn't change. Is it okay? And what do we assume? That this number of non-conformities, obviously in a sample, it is a random variable, and this number means the discrete random variable, and so we assume that it follows a Poisson distribution. That means there will be defects, but the occurrence of such defects is it's the probability of such occurrence is very, very less. Is it okay? So that's why you may assume it to be of Poisson distribution. So this is as per the Poisson distribution. This is the probability that there will be x number of defects in a sample of size n, e to the power minus c to the power x by factorial x. So what is c? C is the average number of nonconformities. Is it okay? So here usual in any textbooks on the quality. The C is this is the term always we use. So that's why it is sometimes referred to as the C control chart. Again, there could be two cases, no standards given. In that case, you have to collect data and you have to compute the average value like C bar. Is it okay? From different samples, and then you determine upper control limit, lower control limit. Okay, the same procedure you follow, the procedure which you have followed for the P control chart. Okay, so again when the standards are given, so the standard is suppose a C0, that you say that this is the number of nonconformities in a sample restricted to C0, say 1 or 2, whatever it is. Is it okay? When the sample size is specified, and accordingly directly you can calculate the upper control limit, the lower control limit, as well as the center line. Is it okay? So this is another example, like there are 25 samples and the sample size remains constant, like say 100 square meter, and this fabric from a textile mill. So this is the area of the fabric is 100 square meter. Now what you try to do, it remains same for all the samples, and you just count the number of nonconformities of a specific type. That means the defects. It's like 5, 4, 7, 6 and so on. Okay, so you have all these data. Then what you do, you calculate the average nonconformities. Okay, and that is C bar, that is 7.560, and then you determine upper control limit and the lower control limit for the C control chart. Again you find that the lower control limit is actually negative, converted into 0. Then you plot all these values, 25, and you find that the 9th sample maybe it is plotted outside of the upper control limit, that is 15.81. So what you try to do, you remove it. That means it is considered to be out of control point. The assignable causes you are able to identify, and when you are able to identify, so you are also able to remove them. So that's why the point is removed. So with this removal, again you recalculate. Is it okay? Now there will be 24 the samples. So you calculate C bar, so that is the center line. Then you calculate again the upper control limit and the lower control limit. Is it okay? So this is the procedure you follow. Now when the sample size varies and you are trying to control the nonconformities or the defects on a particular item, so what you try to do, that means you move to say U control chart, and that is referred to as the number of nonconformities per unit. That means here what we have assumed, in the first case we have assumed that the example we have taken up, that the area of the fabric is 100 square meter. So here what we are assuming, that it may be 100 square meter, 150 square meters and all those. Is it okay? So if you come across such situations, obviously C chart is not applicable. What is applicable is U chart. So that's why it is referred to as the number of nonconformities per unit. So there are many instances where you use U chart, and so how do you compute? So here the parameter is UI, that means ith sample. That means Ci number of say nonconformities, the sample size is Ni. Is it okay? So that means sample size varies across the samples. This is the basic assumptions. So you have to go for UI, and this UI is also Poisson distributed, and then you calculate the U bar when no standards are given. So the sigma Ci divided by sigma Ni. Is it okay? It's very simple one. And now with this, when u bar is known, you calculate upper control limit and the lower control limit. And this is the expression for say the standard deviation. So 3 times standard deviations. Is it okay? On one side for upper control limit, and you subtract that means from say central line or from say the average, that means it lies on the other side of the central line. Is it okay? So this is this way you calculate upper control limit and lower control limit. So this is an example. Like here you will find that the inspected area varies from one sample to another. Like for the sample 1 it is 200, in the sample 2 it is 300, and similarly for all other samples. And then you count the number of nonconformities in each sample, like 5, 14, 8 and so on. So you are considering 20 such samples. Is it okay? Then what do? You calculate the central line. Is it okay? Sigma Ci divided by sigma Ni. So that is 4.683, and immediately after that you calculate the upper control limit and the lower control limit. And so here interesting finding is that the lower control limit is positive. Is it okay? And then when you construct the control chart, so it's the same procedure you follow, the procedure which I have explained with the reference to P control chart. Okay. So this is just an example, the sample size Ni, and then this is the procedure you follow. Please go through these examples. Is it okay? Whatever the formulation, whatever the steps we have discussed with respect to a particular control chart, so those formulations you use and you follow the steps for construction of the control chart. So these details are here. And always what we will try to do, that means first you go for a preliminary control chart, okay, and then assuming that the process is in control, right, then you go for determination of the revised control limits. And so when you determine the revised control limits, assuming that I am creating or I am designing a control chart, assumption is the process is in control. These conditions you have to ensure. That is, before you start constructing a control chart, make sure that the process is in control. Is it okay? So this is the procedure. This is just an example of U chart, this is the idea is that as the sample size varies, that means theoretically speaking, even if you assume say one average value for U, but as the sample size varies, that means Ni is the sample size for the ith sample. Obviously, the upper control limit and lower control limit may also vary. So, what is its impact? That also can be analyzed. That means when you deal with variable sample size, so how many different the alternatives you have for constructing the control charts. So usually there are 4 options. So later on we'll discuss it. That means the variable sample size case we'll be dealing with separately, particularly with respect to control chart for the variables. Okay. Now here, just in short, briefly, I will just explain that how to construct the operating characteristics curves or the OC curves as a performance measure for an attribute control chart. So how do you do it? That means essentially, as I have already explained, that OC curves in control charting means a plot of beta versus the process parameters. So like say suppose it's a P control chart, obviously the process parameter is P. So you need to consider the several values of P, and for each value of P you need to compute beta. Is it okay? So suppose 10 or 15 such values of P you consider, and corresponding beta values also you have computed, and then you just plot them, and by looking at the plot pattern you can conclude that whether the performance of the control chart is all right or not. Is it okay? As you may be recollecting that beta is nothing but the probability of making type 2 error, and you must have sufficient control against type 2 error. So type 1 error is not, even if you ignore type 1 error, as such you may not face any problem. Only thing is, unnecessarily you may be stopping the process and you try to find out some assignable causes, and those assignable causes do not exist. Is it okay? So you may be less productive, but as such there is the assurance that the performance of the product or the performance of the process will not be affected. But if the beta, you do not control this error, the type 2 error, then obviously there could be serious impact. That means suddenly there could be a damage to the process, is it okay, which you may not be aware of, that why it has happened, and it could be a permanent damage to the process. That means what we are assuming, that if the process remains in control state, the process performance will be very high and it will be a sustainable process. So how to compute beta? That means even if at a particular value of p, so what is the probability that the point will be plotted, is it okay, within say a region defined by the upper control limit and the lower control limit. So this is the expression probability that the value of p is less than UCLP minus the probability that the p is less than or equals to LCLP. It's clear? Given a value of p. So this is p hat means x divided by n. So obviously it is x, that is the random variable, number of non-conforming or non-conformities, n into this one. Now n is the sample size, is the sample proportion non-conforming, and the number of non-conforming items. So we are explaining it with respect to p chart. Now n into UCL may not be necessarily an integer. Similarly, n into LCL may not be necessarily an integer. Now obviously the x is an integer. So there will be some the corrections you have to make. That means you say R1 is n into UCL. This expression denotes the largest integer less than or equal to n into UCL. Is it okay? To make it an integer 1, and n into LCL denotes the smallest integer greater than or equal to n into LCL, because this n into LCL is not necessarily an integer. Similarly, n into UCL. So you have to make them integers. So which rule you follow? So you may have this sort of rules. So please go through these rules. You'll very easily you can understand. So what is the expression for probability of type 2 error? That is beta equals to probability that x is less than or equals to R1. R1 is this one. Is it okay with these corrections? Minus probability that x is less than or equals to R2. Is it okay? So there is an example we have. So UCLP is given 0.173, LCL is 0, and the central line is 0.067. So this is then just an application. So with respect to p equals to 0.10, I am trying to compute what is the value of beta. So probability x is less than 50 is the sample size, and this is the upper control limit. So this is 50 is the sample size, and this is the lower control limit. So lower control limit is 0. So ultimately you get these expressions, and you can use say here the binomial distributions. Is it okay? Directly you can use that the probability mass functions or binomial distributions, and then you consider all the possible values, and then you get the value of beta. So so you go for Poisson approximation also. In many a time you go for Poisson approximation to binomial distribution. So if you go for it, so beta is computed as 0.925. That means the probability of non-detection is very, very high. Is it okay? So as the shift from the central line, that means the average across which the process exists. So as the shift magnitude increases, probability of making type 2 error, is it okay, so the decreases. That means the probability of non-detection the decreases. Is it okay? So this is just an example. Okay, so this sort of curve we will get. That means in one quadrant, that means this is the probability of type 1 error, the probability of non-detection of the shift in the process parameters value. So in this case, if it is a P chart, what is the process parameter P? If it is a C chart, what is the process parameter if it is C, if it is the U control chart, what is the process parameter? That is small u, and so on. Is it okay? So this is the procedure of constructing the OC curves for attributes control chart. So later on, when we discuss the variables control charts, okay, so we will refer to other cases, both the general purpose control charts under variables, as well as the special purpose control charts. So in the specific situations, the researchers, the practitioners, they recommend different kinds of special types of control charts. So we will be discussing in the coming sessions. These are the two references you can opt for, where all these details you will get. And then I suggest that as a student, as a learner, as a practitioner, so just go through all the details, and obviously if you have any queries and all, always you can keep in touch with us. Is it okay? Thank you.